Welcome, grade 9s, to our first lesson of our two units on quadratic relations. So I've been kind of hinting on what quadratic relations are throughout the time we were doing factoring. So this is starting to pinpoint what we were actually doing with factoring. We were often talking about quadratic relations. So let's start off with a couple of definitions. Our first definition is, what is a quadratic relation in standard form? Keyword there, in standard form. An equation in standard form, y equals ax squared plus bx plus c, c being the y-intercept, where a, b, and c are real numbers and a doesn't equal 0. Translation. So these values here, a, b, and c, they're going to be real numbers, not decimals. They can be fractions, but that's about it. That's going to be in standard form. A has to be a number that is not equal to 0. So it can be bigger than 0, smaller than 0, but it cannot equal 0. If it equals 0, this x squared gets canceled out, and the whole thing of it being a quadratic doesn't happen. You need that x to the power of 2 for it to be a quadratic. Now, quadratics are usually in the form of a parabola. A parabola is a symmetric U-shaped curve / graph of a quadratic relation. So they're quadratic relations and they look like either this or this. They're U-shaped, not quite a U, but they are shaped like a U. So what we're going to start off is by looking at the basic parabola, which everything else is an expansion of it. So this is your basic parabola, x squared. So what we're going to do first is create a table of contents, a table of values for x squared. So let's start with, this first one here. We have y equals x squared. So we're going to put the 3 where the x is, so we get 3 squared equals 9. 2 squared equals 4. 1 squared equals 1. 0 squared is, 0 times 0 is 0. Negative 1 squared. That negative is within. So negative 1 times negative 1 is going to give you 1. Negative 2 squared. Negative 2 times negative 2 is going to give you 4. And negative 3 squared is going to give you 9. If you notice here, the negatives cancel each other out. So this is the same value as here. Here and here. Here and here. Here and here. So let's start by saying what these points are. If we were to say, put these in our Cartesian point system. What this one's going to look like, x is 3, y is 9. X is 2, y is 4. X is 1, y is 1, 0 and 0. That's called the origin, by the way, wherever it starts off with. Origin. Negative 1 and 1. Negative 2 and 4. And negative 3 and 9. So we're going to plot these points on our graph. 0 and 0. 1. Negative 1. 2. 4. Negative 2. Also at 4. 3 at 9. And 3 at 9 as well on the other side. And we're going to connect them as best we can. It's going to look something like this. It's going to be very hard initially for you guys connecting the points. That's okay. It takes a little bit. Just keeps going off. Kind of looks like a U. Not quite like a U, but pretty close. And we just want to put our arrows at the end here because it's just going to continue off in that same pattern. So how do we identify quadratic relations? So say if we just had a table of values and we're like, does this table of values depict a linear equation, a function, a quadratic? We just have this table of values. We don't know. So one way we can look at it is first differences. So you take the differences between consecutive y values. So a relationship is linear when the first differences are the same. It's one thing we need to know about first differences. However, with second differences, we're looking at the consecutive differences between the first differences. So we'd be subtracting one from the other. A relation is quadratic, aka when the second differences are the same, are constant or the same. You can use either way. That's how we can tell if we are looking at a table of values and we don't have a graph. We want to see if these equations that were given, this information, are first or second differences. So let's try a couple of these out as an example, because words are great, but that might not translate into something that we can understand. So here we have a table of values. What we're going to do is take this one and subtract it from the one above. That's going to give us 1. We're going to do the same thing again. 6, we're going to subtract the previous one, 3, which is going to give us 6 minus 3 gives us 3. We're going to take this guy here. You can kind of see how we're going this one, subtract this one, then subtract from that one. So here we're going 11 and we're subtracting 6. So 11 minus 6 gives us 5. Next one, going with 18 minus 11, because we're taking this one and subtracting the previous, and that's going to give us 7. So if we're looking at these here, these aren't constant. So we know right now that this is not a linear function. If they were the same, it would be linear. So what we're going to do is check the second differences. And how we do that is we're going to do basically the same sort of idea, but we're going to take these away from each other. So we're going to take 3 and subtract 1 from it. So 3 subtract 1 gives us 2. Same, we're going to take 5, subtract 3, gives us 2. And then we're going to take 7, subtract 5, and it gives us 2. If you notice here, these are the same. And if our second differences are the same, that means that our function that this table of values is depicting is a quadratic relation. So therefore, this is a quadratic relation. And let's put a y, because the second differences are constant or the same. So this means we have a lovely graph that kind of looks like that, a U. And because the second differences are the same, this quadratic is going to open up. We'll discuss one where we have something that opens down. So opening of a parabola, what that means is what direction it is opening. Is it going up or is it going down? So if A is greater than 0, the parabola is going to open upwards, meaning that it's going to give us a minimum. So that would be like if it was 1 or 3 or 19. But if parabola is less than 0, i.e. a negative number, If the parabola opens downwards, the second differences are going to be negative. Let me restate that again. If a is greater than 0, the parabolas are going to open upwards. And if the parabola opens downwards, you're going to have second differences that are negative. So that would be like saying that we've had a negative x squared as our parabola. You'll see more of this as we continue on. What we're going to do now is graph and check out the second differences of y equals negative x squared. So what we're going to do here is put in our x values, have 0 here, 1 and 2, -1 and -2. So 2 squared, because the negative is on the outside of this, so we have 2 squared, like that. -2, so we do the squaring here first, which is 2 times 2, and that's going to give us 4. So the negative stays on the outside. So 1 squared gives us 1, and then we put the negative in front of it. 0. -1 squared gives us 1, and then we add the negative from in front. This negative is added on last, okay? -2 squared gives us 4, -4. So what we're going to do here is now check out the first differences. So we're going to have -1 subtract, bracket, -4, which really equals -1 plus 4, which is going to give us 3. 1 minus 0 minus -1 is going to give us 1. -1 minus 0 gives us -1. -4 minus -1 is going to give us -3. Okay. These guys are not the same. So since they're not the same, we know that the first differences, so they're not the same, these first differences don't give us the same number. We know that this is not a linear function. So we're going to now go check second differences. So we have 1 minus 3. Then we have -1 minus -1. This is -2 again. -3, that comes from here. Subtract -1. So -3 plus 1. Two negatives cancel each other out, and we get -2 still. Now, we notice that these are all the same. They're also negative. So since we know that the second differences are negative, we're going to notice that this parabola opens downwards. And what I mean by that is if I plot these points, you're going to see it. So got at the origin, 0. Then -1, we put it at -1. +1 goes at -1. Go to -2, and that's going to give us -4. Same thing on this side. Go at one more, it's also going to be at -9. And we connect the dots. Which is a lot harder than kind of looks sometimes. So if it takes you a while to get this all straightened out, don't worry, I'm not going to take too many marks off. These aren't looking perfectly neat. So when you have a negative a, it's going to open like this. It opens downwards. It's going to have a maximum point because nothing's going to be bigger than this point. But if you look up on the other one, where we had a being positive, it opens upwards. Everything goes bigger. And this here is what we call a minimum. We'll move more into that in a minute. All right, so here we have a chart. Determine the missing values of this chart. I'm going to get you guys to pause this video and try it. See where you get with it. Okay, so this one's saying determine the missing values in the table. We know that the data is quadratic. That's a key information here. Quadratic. What that means is that the second differences are going to be the same. So we can already fill in these guys here. These are all going to be 2. Now we're going to move backwards. We know that something minus 3 is going to give us 2. So we have something minus -3 gives us 2. I'm putting an X here because I don't know what that value is, so we're going to go solve for it. If I have X here, we're going to bring that -3 over to the other side. Actually, before I get there, let me remind you of something. Negative and a negative equals a positive. So we got X equals positive 3. If I go over here, X equals 2 minus 3. X equals -1. So that is what this value is. I'm just going to put in a different color, nice big so you guys can see it. This section here is -1. So we know this value is -1. Now we need to do the same thing for the next one. We need to figure out what is missing here. We have something minus -1, that's the number above here, gives us 2. X plus 1 equals 2. These two negatives cancel each other out. The reason I'm saying something is because remember, it is something subtract is the number before subtract the previous number to get our second differences. So we're taking our previous first difference and we're taking our previous number first difference and subtracting it from the last one. So we got this current first difference and we're subtracting the last first difference to give us the second difference. So what we end up getting is X equals 2 minus 1, which is going to give us 1. That means this number here is 1. We're going to do it one more time. X, we don't know what this number is. What is in this particular box, we don't know what that is. And how we got this number here was this number minus the previous number, which was 1. And we know it's going to equal 2 because that's what this equals. So X equals 2 plus 1 when we bring this 1 over to the other side, which gives us 3. So we now know that this number here is 3. We're going to do the exact same thing for this number. Okay? We have a value here. This X, we want to know what's in this box. We know that this number that's in this box here, subtract this number here, which is a previous number, is going to give us 3. So X equals 3 plus 5. One thing to always remember, we need to watch our negatives. So negative here, negative here. So -3 plus 5, because this is a -3, gives us 2. We're going to do the same thing again. So that means this number here, remember, is 2. Okay, so for this next one, this box here, sorry, I have my drawing tool on for that one. That doesn't work very well. We want nice looking 2. Okay, again, what we know is that this box here is equal to So we're saying that this box is represented by x right now is equal to x minus the previous number, which is 2, equals our first difference, which is -1. So x equals -1 plus 2, which is going to give us 1. Now, we're going to check the next one, see where we're going. Same sort of idea. This box that I'm looking at right here is equal to this number. Sorry, I'm saying that very awkwardly. Let me try that again. This box here minus the previous box equals 1. So this box minus the previous box equals 1. So x minus 1 equals 1. So x equals 1 plus 1, once we were equals 2. Okay, if you're starting to notice something with our quadratics, this would be the base, and if these two are the same, that means this number is going to be the same here, because they are symmetrical. It's important to remember. Quadratics are symmetrical. One side will equal the other. So if you find a moment where you have a bottom and the next two equal the same, you know that the next number here and here is going to be the same down here. This is 5. So this is how you can work backwards. It will take a little bit getting used to, but you will get it after a while. So what we're looking at here is the relationship between the dots and the quadratic relation. As these dots get bigger, you're going to know something. You have 1, 2. Figure 1. Okay, I'm going to go to this. Figure 1 just has 1 dot. Figure 2 has 1 dot here, and 2 more from the previous. Figure 3 has 1 dot here, 2 from this one, and then an additional 3. So there's 1, 2, 3, 4, 5. 5 here. And in figure 4, you have the same from figure 3, the 1, 2, 3, 4, 5, but now they're adding an additional 4. So 5 plus 4 gives us 9. Figure 5 is going to add 5 at the bottom. So you're noticing they're just adding another stack to keep this becoming a larger triangle. So 9 plus my apologies. Let me just go back here for a second. I counted wrong on one of these. It's not 5. 1, 2, 3, 4, 5, 6. There we go. And then 6 plus those additional 4 here gives us 10. We're going to add 5 for figure 5. So 10 plus 5 is going to give us 15. And then 6, we're going to add an additional 6 at the bottom of that row, which is going to give us 29. So how we're going to prove whether or not this is a quadratic function is by looking at first and second differences. So we're going to have our first differences here. And then we'll put the second differences in the next column. So we're doing this here. We're going to look back. So 3 minus 1 is going to give us 2. 6 minus 3 is going to give us 3. I'm going to show you just a little bit differently so you can see this. These two are going to give us 2. 6 minus 3 is going to give us 3. 10 minus 6 is going to give us 4. 15 minus 10 is going to give us 5. And 21 minus 15 is going to give us 6. Looking at the other one, we're going to be doing the exact same thing. We're going to take these two, 3 minus 2 is going to give us 1. 4 minus 3 is going to give us 1. 5 minus 4 is going to give us 1. 6 minus 5 is going to give us 1. Since we know these second differences are the same, we know that this is quadratic. What I want you to do is pause this video and do a couple of these practices to make sure you're starting to understand the information here. So once you come back from doing those, you can continue on with the video. So we've been looking at first and second differences, comparing linear and quadratic relations. In a linear relationship, the first differences are constant. That's really important to remember. Linear relations will have constant first differences. So in this one here, this is a linear relation because we can see that the first differences are constant. They're all -3's. However, if the first differences aren't constant and we go to look at the second differences, a quadratic relationship, the second differences are constant. This provides that the first differences weren't constant. So if you see that the first differences aren't constant, you can go, I wonder if we take the differences of these first differences and go find their differences to find the second differences, will those be constant? If these are constant and the first differences are not, then we have a quadratic relationship. So let's look at the difference between a linear relationship and quadratic relationships as graphs. Looking here, the linear relationship is just a straight line. But a quadratic relationship is a parabola, almost like a U. It's symmetrical. So you could plop a line right down the middle, like so, and fold it in half, and these numbers are going to be in the same spot. They're perfectly symmetrical. You cannot do that with a linear relationship. Lastly, equations. So here is the equation of a linear relationship in y equals mx plus b format. This is what it looks like. There's only one x. There's nothing squaring this x. There's technically a little 1 up here. Looking at a quadratic relationship, it's a little bit different. We have y equals ax squared plus bx plus c. You'll notice the leading x here is squared. That's important. If you see this x squared without anything in front of it, so like not an x to the 4 or an x to 3, this is going to give you a quadratic relationship. You need to make sure though that a does not equal 0, because if a is equal to 0, this entire expression goes bye-bye. Because anything times by 0 will give us 0. So then there is not an x squared. So let's look at a couple more. Here we have properties of graphs of a quadratic relationship. So here are some definitions. Why don't you go read over these and see what you think the most important point is. So pause the video and do that. Okay, welcome back. If we're looking at the different definitions that are important when we're looking at quadratic relationships, the first one is a vertex of a parabola. If a parabola opens upwards, so that means it's going up, looks like this bad boy, U pointing the up direction, the lowest point of the vertex is the lowest point on the graph. So it's going to be this bad boy right here. That's the lowest point of the graph. If a parabola is opening downwards, the vertex is the highest point of the graph. So downwards. So we're going to look at this guy. Looks downwards. And the vertex is the highest point of the graph. The vertex is represented by the order pair H and K. You will see what H and K mean when we see a different version of the quadratic relationship. So right now we're looking at it in standard form. You'll understand what H and K mean when we start looking at something called vertex form. Hint, hint, nudge, nudge, that will come later. Maximum, minimum. So a maximum minimum is when the maximum or the minimum is the y-coordinate of the vertex. So think about it this way. In a graph, if it's opening upwards, this guy right here, that's your vertex. Everything after it is going to be above it. So that means this is your minimum. If you're looking at the other one, everything below goes below it. So that's your maximum point. This is also known as the optimal value. It's either your highest or your lowest. That's important to remember. So if the vertex is H and K, then the optimum value is its K value. This guy right here. Zeros of a quadratic relation. The zeros of a quadratic relationship are its x-intercepts. We've actually started already looking at these, whether we realized it or not. If the zeros are represented by R and S, the zeros are written as an ordered pair, R0 and S0. For a quadratic relationship in the form of ax squared plus y plus bx plus c. Therefore, the zeros of the quadratic relationship are the values of x when y equals 0. To calculate the zeros of a quadratic relationship, you set the y equal to 0 and solve for x. It's not always very simple, and we'll get into how that is in action a little bit later. Axis of symmetry. So the equation of the axis of symmetry of a quadratic relationship is the equation of the vertical line that passes through the vertex. So that's the important part. It passes through the vertex and it right in the middle. The vertex is represented by HK. We remember that. So the equation of the axis of symmetry is x equals h. If two order pairs on the quadratic relation have the same y-coordinate and are represented by Pn and Qn, so this is really complicated to explain with this sentence. Right here is how we can find the axis of symmetry if we can't see it right on the thing. What we're going to do is take 2 points on either side of the graph where they have the same y-coordinate. So they need to have the same y-coordinate. So we add P and Q together and we divide by 2 to find this middle guy. The axis of symmetry can also be determined if you take the two zeros of the quadratic relationship and just add them together and divide by 2. You take the average of them. So this equation right here is one you should know. It's going to be important. I will be asking you to calculate the axis of symmetry using this. So let's start labeling this graph. Right here we have a quadratic. It's pointing to different parts of what we need to know. So let's start looking first at the vertex. The vertex is down here. Our vertex is represented by the x value, which is -1, and y value is -4. So that is our vertex. So from that, the x value of our vertex is our axis of symmetry, our AOS. The axis of symmetry right now is this green line. So we can already create our equation. Remember, x equals h. And our h here is our axis of symmetry, or our x value of the vertex. So x equals -1. That's our axis of symmetry. Our optimum value is the y value of our axis of symmetry. So it's also known, sorry, not our axis of symmetry, of our vertex. And that is also known as our optimal value. So our optimal value here is y equals -4. And because it's opening upwards, everything else here is going to be bigger. This means that our optimal value is a minimum. And last but not least, we need to look at our x-intercepts, or where our parabola passes the x-axis. In this case, it is 1 and 0, and -1 and 0. So that's just how we label all these lovely information here. So what I want you guys to do, pause the video, try to label everything that you can from here. Once you have tried that, come back and see what the answers are. Okay, so let's go through these. Our vertex is the lowest or highest point of our graph. So if we're looking at this first one here, our vertex is right here. It's our lowest point in the graph. It's at -3 and 1. Is it max or a minimum? We look, is everything going above it, or is everything going below it? In this case, everything's going above it. So this is our lowest possible value. So therefore, it is a minimum. Our axis of symmetry is always going to be our x value of our vertex. And since our vertex is an x value of -3, we can say the axis of symmetry is x equals -3. Our zeros. Our zeros are where the parabola crosses the x-axis. If we look at this parabola here, what you'll notice is that the lowest point is above the x-axis. So that means it's never going to cross the x-axis, which means there are no zeros. None. Okay, direction of opening. Is it opening up or is it opening down? Since we have a minimum and we can see that's opening up, we can say that is opening up, going positive. Y-intercept. Let's go look where this is passing through the y-intercept. So, not perfect. We need to look approximately where it's crossing this y-axis. It looks to be around 7. So we can say that our y-intercept is 0, 7. Okay, let's try this again for this one. Okay, axis of symmetry, our vertex is down here at -1 and -4. Looks like it's moving up, everything's above it, so this is a minimum. Since we notice that everything is moving up, we can also write our direction of opening as up. Axis of symmetry is always our x value of our vertex, so x equals -1. Zeros, does it pass through the x-axis this time? Yes, it does, and where it does appears to be +1 and -3. So those are our two values. So we can write it as -3 and 0 and 1 and 0. There's 2 points where it crosses. And our y-intercept, let's see where it crosses. It looks to be around here, so that looks like -3. So 0, -3. We're going to do the same thing with this one. Our X, our lovely vertex is up in the sky. And that looks to be about 5 on the Y, it says here, and -3 on the x-axis. So we get -3 and 5. Everything is going down or and away. So this is going to be our max. Looking for our axis of symmetry. Remember, it's always going to be the x value of our vertex. So then that means x equals -3. Do we have zeros this time? We do, but they're not crossing at nice, perfect ones. They're kind of crossing at, switch. There we go. They're kind of crossing a little bit off. So we're going to kind of guess about this. This one looks like about 0.9 to me, and this one's like a little bit bigger than -5. So let's go with -5.1 and 0 and -0.9. So that's a negative. Let's make that a bit positive. When you're looking at the graph, try your best to get as close as possible, but you're sometimes going to have to guess. Direction of opening. Well, these ones were opening up because we had a minimum. This time we have a maximum, so that means it's going to be opening down. And last but not least, we need to look for our y-intercept. So let's kind of zoom in here. Kind of looks around -4, so let's go with -4. So 0, -4. Here's some more practice in your document for you to continue and try out. And what I want you to do here is a bunch of assigned homework I want you to try out, okay? This is homework. Try it out.